Hello everyone, today I'm presenting the abstract improving the performance of integrated RF-B0 shim array using 3D coil elements with orthogonal loops. I have nothing to declare. First, we'll have an introduction on the integrated B0 RF shim coil array for shimming and signal reception. The shimming of B0 field is essentially NR imaging because B0 field inhomogeneity can reduce the effectiveness of RF pulses, resulting in signal voids, blurring, and image artifacts. Integrated RF shim coil arrays offer capabilities for concurrent parallel RF reception and local B0 shimming. Existing 2D AC/DC arrays have drawbacks of inflexible shim field patterns, limited shim strength, and degrees of freedom. From signal reception perspective, 2D AC/DC array may have limited depth penetration for signal reception, especially for a large number of small coils. In our novel 3D coil geometry, each 3D coil element has a main loop and an orthogonal Y loop to realize decoupling. 3D coil elements with orthogonal X and Y loops will be able to improve SNR and depth penetration as well as spatial sensitivity distribution compared to standard 2D coils. The 3D coil topology may also benefit B0 shimming performance by providing new degree of freedom with orthogonal shim array compared to existing 2D arrays. The goal of this study is to simulate B0 shimming performance of our novel 3D orthogonal loop coil arrays and to compare the result with standard 2D arrays. We designed two AC/DC array with 3D orthogonal loop geometry. First one is 2D loop coil array plus 45-degree neighbor orthogonal rectangular group, which is known for its capability to model neighbor-wise orthogonality. The second one is 2D loop coil array plus parallel to B0 orthogonal rectangular group. This is more favorable for signal reception but weaker for B0 shimming. Here's our 3D coil array shimming results simulation details. To simulate the current, each loop coil is approximated by 64 equal length vectors as the coordinate origin. To move each coil to the correct position around brain, the start and end point of each vectors are also recorded for later projection. The magnetic field generated by coil current is calculated by Bell-Safart solver. Genetic algorithm is applied to optimize the coil current in the arrays to maximize the B0 field shimming performance. In our coil subarray selection study, coil subarray selection is performed with certain percentage of largest currents kept to study 3D coil array performance compared to 2D one. To evaluate the shimming performance of 3D coil arrays, the result of 3D coil subarrays should be compared to a 2D one with twice number of coils because each 3D coil have 2 times of loops than a 2D one as is shown. The 3D coil subarray selection result is here. Here's the shimming field map of 2D geometry with all coils selected. Here's the 3D coil subarray shimming result bar plot. By observing the bar, we can draw the conclusion that in general our 3D array with 45-degree neighbor orthogonal loop is superior to that with parallel to B0 orthogonal looping shimming. Both of our 3D coil geometry yield better shimming result than that of 2D one, which is expected since each 3D coil element is composed of 2 separate coils, which each 2D element only contains 1 coil. For small number cases, the result of 3D arrays with 45-degree neighbor orthogonal geometry is still superior to that of 2D arrays, even with only half of the coils selected. For large coil number cases, we can only get small to little benefits for B0 shimming use 3D arrays in comparison with 2D one. However, 3D coil array may have benefits in SNR depth penetration and J factor over 2D arrays in most of the cases.